Hello everyone, this is Ishwaki Thakkar and I'm going to present the project on the LMS adaptive filter. So the contents which are included are the introduction to the whole method, the architecture of how the design is implemented, how the design is implemented in the MATLAB and Altera, the methods of all that, and finally the conclusion. So what is filter? So the figure is, as you can see, the method in which any noise is filtered by some of the algorithms, and the final signal is what is expected and what is needed. So that is called a filter. So the usual method of estimating a signal corrupted by a noise, and when you pass it through a filter, it suppresses the noise and leaves the original signal which we want. So now, what are the types of filter? There are two types of filters, fixed and adaptive. So what are fixed filters? For the fixed filters, you need the knowledge for signal and noise. You need those two inputs. And when you have the signals and noise, when you pass those two signals through the filter, you can obtain the signal which is expected, as I just explained. And it rejects the frequency, and like for the low pass band or the high pass band, it rejects those frequencies which are the noise. So what are adaptive filters? For the fixed filters, you know the signal and noise, but the adaptive filters are such filters which have the ability to adjust their response according to the correlated feedback. So in these filters, you don't need to have the knowledge of the signal and noise as it was required in the fixed filters. So, in as shown in the adaptive filters, when you have the signals, the real signals from the environment, it adapts itself according to the noise, and it removes the noise itself via some algorithms. We'll look those algorithms in details later on. So it adapts the signal, and you can get this kind of signals in non-stationary conditions. The conditions are not stationary, so the noise keeps on changing, the coefficients keeps on changing, so we have to get the algorithm accordingly. Now, what is noise cancellation? So as I told you, because there's it's the real signal, there will be noise, so we need to have some algorithms for that. So the noise filtering is done when you pass the signal and noise through some of the algorithm, and then you pass the reference signal through some filter, and when you add those signal, so the noise gets subtracted, like here as shown in figure below. So S plus N is signal plus noise. Now when you send some reference signal through a filter which is noise, well, you have to take the feedback from the environment, you have to find the noise signal, you have to send that signal through the noise, and when you subtract that from the original signal, you get the signal which is expected. So here the S plus N, you get S cap, right? And when you pass the noise which is filtered and then subtracted, you will get S plus N minus N. So obviously this is not the most efficient and it's not 100% accurate, but you get almost the original signal by this algorithm. So now what are the problems in noise cancellation? So when you subtract the noise from a received signal, there are the chances that you are distorting the original signal also, and that can increase the noise level. If you don't filter the perfect noise signal, so some extra white Gaussian noises and other noises gets added up in that. So your original signal is lost. You can totally lose your original signal. So it is very precisely needed that you should calculate the noise, exactly the replica of the noise. Hence, the algorithm should be such that it should get the actual accurate noise so that you can get the real signal. Now, as I said, that when the noise is not properly captured, there are problems of the distortion of the signal. So what is the solution? The solution is, when the adaptive filter is used, it adjusts itself the impulse response from the error signal, and then it gives that to the output of the filter, and hence you can get the signal which is expected. So there are the filter weights and the impulse response which are responsible for the adaptive algorithm. So hence noise reduction is accomplished by the adaptive filtering, and adaptive noise cancellation makes the possible attainment of the noise rejection levels that are difficult or impossible to achieve by direct filtering. In direct filtering, as I said, that the all the signals are known, but in this, as it is unknown, we the need of adaptive filters comes into the picture. Noise cancellation has been used in the real world also. I can give you one small example, like when you're talking on a phone and there are some background noises. There are already the filters and the algorithms inside your cellular phone which cancels the noise which is not needed from the other hand side. As you can see in the below figure, there is a far end signal and there is echo which is captured again by the microphone. So when they are providing the signals from the loudspeaker, the signals which is extra, which is error, the echoes are already being subtracted by the feedback loop to the adaptive filter. So the adaptive filter at a certain point, it adapts to the errors and it converges it to most zero possible value. So the noises takes time to converge, but it converges by using adaptive filters. With this adaptive noise filtering method, there is low risk of the noise reduction, like low risk, I'm sorry. With the adaptive control, the noise reduction can be accomplished with little risk of the distorting the signal. So you can achieve the maximum expected signal from this algorithm, which is never achieved by direct filtering because the error signal is converges in the real environment. It adapts at each and every second with respect to the original signal. So the algorithm which is used for the adaptive filtering noise cancellation is linear mean square algorithm. There are many other algorithms also, but we are choosing linear mean square algorithm. You can see the information regarding the linear mean square algorithm. So how this the adaptive noise cancelling process takes place? As you can see in the figure, the signal source is S, which is combination of the real signal plus the noise. So S plus N goes to the summation block, which gives you the output. Now, the output is controlled by the adaptive filtering. So the output signal goes into the feedback loop in the adaptive filter in the form of error. What does this vertical arrow in the adaptive filter means? It is not straight, it is little slant. That means that the this adaptive filter has some coefficient, has some factor which affects the above process. It doesn't directly affects the process, but it somehow indirectly affects the process of the filtering. Hence the error signal from the adaptive noise get some coefficients which are applied to the signals and the noise, so in order to get the real output. As we can see that the noise source is sent to in a form of X to the adaptive filter. The error signal is also sent as a feedback loop from to the adaptive filter, and hence the final output is obtained. So I have given some information regarding the noise cancellation. So a single channel adaptive noise canceller with uncorrelated noise M0 is present in the input. So we can see that here this M1 is given to the input to the adaptive filter. So the primary input does consist of a signal and two noises, M as well as N. So here we can see that S plus N along with M is the input to the environment. So hence the total noises are there which can be avoided by the H, that's the coefficient of the adaptive filter. As I said that there are some algorithm which gives the coefficient which indirectly affects the original signals. So the Wj here are the coefficients from the adaptive algorithm, and Sj plus drift are the noise plus the original voice, and hence the adaptive algorithm helps to get the output which is expected real signal. So this is the algorithm shown, or the architecture of the whole LMS adaptive filter. The X are the inputs, H of j are the coefficients, Y of j is the output which is expected. So the D of j is a desired signal. So desired signal is along with the noise, it is sent as a feedback, and mu is obtained. Mu is a error coefficient, and by some LMS algorithm you can obtain H, which continuously updates. As you can see, the X has the delay shift registers, and H are continuously updated. And I will show in the coming slides that how exactly this operations takes place. So now let us go to the design, how I implemented the whole LMS process. So first of all, I checked the code of convergence, how it took place for the error signal in MATLAB. So in MATLAB, I wrote one code, and the implementation was shown as how the error signal gets converged. And when you change the tab filters, the number of tabs, I'll come to the step of what is tab filter also. And so when I change the number of tabs of the filter, it converges faster or later according to the number of tabs. So when I check the convergence of the error signal in the MATLAB, I then implemented the Verilog code on the Altera Quartus tool, and to see the behavioral simulation in Modelsim. So as I said, the tools which were used were MATLAB and Altera. MATLAB was checked for the functional verification, and Altera tools were used for the simulations. So I'll show you what are the graphs which are obtained when the input signal x of n and the desired signal d of n were given as a random signals. I generated the set of 1,000 random signals which were given as input x of n and d of n, and the x and d are filtered with coefficients, and hence the filtered output were given as an input to the LMS algorithm, which was the architecture which I showed before. So the graphs which were obtained were in MATLAB. The graphs were, when this is x plot and this is the expected results, this is x, this is the desired signal, and this was y output signal. So you can see that the d is with the noise and y is without noise. So I'll show you the error signal. This is the error signal. So as you can see that the error signal got converged around nearly 350. Here the tab used was 24. For the 24 tab filter, for the 1,000 samples, you can see the 1,000 samples, it got converged around 350. So as you can see, the error signal goes on reducing itself with the time, and it finally converges to 0. Now let us go to the Altera implementation on the Quartus tool. Uh, So what implementation method I used? As I said, the inputs and the desired signal which are filtered are generated from the MATLAB itself, and we change that to the binary form, a binary floating point form, and those were given as 1,000 input samples to Altera in the test bench. Now the algorithm for LMS was written in Verilog in Altera. So what happens is that the delayed inputs are multiplied with the coefficients which are updated, are multiplied with the old coefficients, and the results updated is the new coefficient. So LMS algorithm filter everything makes adaptive filter. Also, as I said, that 4-step filter was used. That means that the input signal is delayed 4 times, and 4 times the coefficients are multiplied, and the output which are obtained as y1, y2, y3, y4 are added together to get the final output. So for the 4-step filter, 4 inputs are multiplied along with the coefficients. Now I'll talk here about the number of cycles also, and how the errors and coefficients are generated and multiplied. Now, as I said, that the number of cycles it takes to give you the expected output, it's always 2 more than the number of tap filters. We can see that delay is one cycle, the flop or register used, so it is of one cycle. So at first, as the first delayed block is updated, still the second, third and fourth block are yet not updated, and they are 0 as they are initialized to 0. So on the second cycle, the second delay block is updated. On the third cycle, the third delay block is updated. And on the fourth is updated. But here, what is the case that the coefficients which are multiplied, you cannot get the coefficients directly. You always get the coefficient after the error signal is obtained. Now, even the error signal is not obtained in the first cycle itself because everything is initialized to 0. So on the first cycle, the error signal is obtained, and on the second cycle, the coefficients are obtained. And after this phase, the actual filtering starts, and you can start receiving the outputs. Till then, y of n is always equal to x of n. That is, output signal is always equal to the input signal. So as we use 24 step filter, it took 24 plus 2, that is 26 cycles. So as you can see that in first case, it is assumption that first see the last case. The assumption is E of 0 equal to D of 0 minus Y of 0. Everything is 0 first. So it is 0. On second cycle, E is updated. So also on the first stage, the W new of 0 equal to W old of 0 plus mu into error signal into X of 1. So the error signal gets updated on the second cycle, and then as you can see in the calculations, the W new is updated as well as the Y of 1. The outputs are updated. So W new is W old plus mu E into X, and Y of 1 is Y of previous, that is Y of 0 plus W new, which is the updated 0 of the previous stage, into X of 1, that is present signal. You can see that in second stage, Y of 1 equals to Y of 0, that is previous stage output, plus W new, which is obtained from first stage, into X of 1, which is present state input. The test bench, as I said, were given from the MATLAB. So input signal and desired signal were given from the MATLAB, and thousands such samples were given to obtain the simulation proper convergence of the in the simulations. So I'll show you the simulations of my project. So as you can see, the first signal is clock, the second is reset, the third is the error signal. You can see that as we obtain in the MATLAB in functional verification, it is almost same as that. The error signal gets converged slowly to 0, and it is not getting completely 0. There are errors coming always, but it is almost getting to 0. And the below figure are of the desired signal and the input signal. So this is just the information about my simulation results and how are the inputs given and how the error signals got converged for the 24 tap filter. So I want to conclude my session that we look to the LMS theory, how the filters work, how the adaptive filter work, what is noise cancellation, what are the algorithms for the noise cancellation. And in the project, we saw that in MATLAB first the error signals got converged when the inputs and outputs were given with the samples and the number of tap, and then the same was implemented in the Altera, and we got the simulations accordingly. Thank you. This were the references from where I got all the details of the project. Thank you so much.